Previously, we actually jumped ahead in the text in section 8.3 of your text, confidence intervals for P. I'm going to retreat now to 8.1 and 8.2. Confidence intervals for mu. Now, it's important that we know the difference between the two, and in reading the context of a problem, we should be able to distinguish exactly what the problem is looking for if we just, instead of trying to plow into what buttons do I push on my calculator, take a moment, read the problem, and see what we're after. P is a probability or a proportion. Proportion of voters who think Gavin Newsom's doing a good job. Probability that a thumbtack lands pointy side up. Proportion of 17-year-old boys who've smoked cigarettes in the last month. Proportion of community college students who are finding it more difficult to take math classes online than when the classes were face-to-face. So P is a proportion. Mu is the average. Mu is an average. Average height of adult women in California. Average number of sleep that 19-year-olds get on a Saturday night. Average number of units that a community college student is enrolled for this semester. So mu is we call it the population mean. More common language, you're used to calling that an average, as opposed to a probability or proportion. It's always going to be between 0 and 1. Now we're looking for an average. Okay. We had point estimate for P. We called it P hat. Number of successes over number of trials. Point estimate for mu. Remember, mu represents a population mean. And if I'm trying to find a point estimate for mu, kind of common sense, I'm going to take a sample and find the sample mean, and that's my best guess for the population mean. And X bar, if you've got raw data, sum of the x's over n, more often than not in a problem we're just going to give you X bar, but you could be given raw data and be asked to find, actually find X bar. Confidence interval for P, we started with our point estimate, P hat, and then we said, you know what, P hat might not have nailed P exactly, so I'm going to expand on either side of P hat, grab a portion of the number line, grab an interval. I'm going to subtract and add an error estimate, E, to it to obtain an interval. And we've done those to death by now, hopefully. What's new here? Confidence interval for mu. We're going to start with X bar and then subtract and add some error estimate. Now your book calls this a dead pen. Your book calls this EBP, error bound for proportion. They call this EBM, error bound for the mean. I'm not really changing notations. I'm just saying E for error estimate. So just realize if you're reading the text, you're going to see that notation that's going to be slightly different. Okay. So, again, more often than not, you're going to be given X bar in the problem. If you're given some raw data, you could go ahead and find X bar. The big question is, how do we find E? Now, in 8.1, we find the error as the z-score that leaves alpha over 2 in each tail. Same as before, and you're experts at this, hopefully by now, times sigma of x bar, where sigma of x bar, we learned, is sigma over root n. And you could read through section 8.1, and they'll give you a bunch of problems. And I'm going to suggest, well, let's not even bother with the problems out of 8.1. Now, the reason they do that early on is to get you used to the mechanics of doing a confidence interval. I think we already did that by putting confidence intervals for P first, is we got the mechanics down. These problems assume we know the population standard deviation. And this is why I find those problems to be kind of hokey. We're trying to estimate mu. We're trying to estimate a population mean. Well, we're trying to estimate the population mean because we don't know the population mean. And if we don't know the population mean, it's a pretty safe bet that we don't know the population standard deviation. Okay. So, since we likely, in fact almost always, don't know sigma, we substitute S and use, I'm going to call it S with the subscript x bar, which is going to be our sample standard deviation over the square root of n. Seems kind of logical and similar to what we did before. I don't know sigma, the population standard deviation. I do have some data. Most of these problems, somebody else crunched the data for you and gave you the sample standard deviation. But if you had the raw data, you could find the sample standard deviation, still divided by root n. So all we've really done was substitute S here in place of sigma, and we're calling it now standard deviation of x bar, but sample standard deviation of x bar, as opposed to using sigma, the symbol for population standard deviation. So people started doing this merrily going along and saying, I'm going to make my error a z-score times, and I'll just use S of x bar instead of sigma of x bar. And they started going merrily along making confidence intervals. And after a while, they discovered this didn't quite work. And here's the reason why. We're using S in place of sigma, but S is usually smaller than sigma. That is, the amount of variability in my sample is usually less than the amount of variability in the entire population. So what was happening, S was too small, this was a little bit too small, my error was a little bit too small, and so my confidence interval for mu x bar plus or minus e, people were making 95% confidence intervals and finding they weren't correct 95% of the time. They were making 90% confidence intervals and finding they weren't correct 90% of the time. And the problem was S was a little bit too small, so this was a little bit smaller than sigma of x bar. We weren't getting a big enough E. We weren't making a wide enough confidence interval, and my 95% confidence interval wasn't right 95% of the time. So we're going to make an adjustment. Now, we'll make my error a t-score that leaves alpha over 2 times S of x bar. We're using a slightly different distribution. And for our purposes, we can think of the t distribution as a tweak. It's kind of a slightly different than the z distribution. So we're doing this instead of e being z of alpha over 2 times sigma of x bar. This is what we'd like to use, but we can't because we don't know sigma. We started substituting s, but we found s was a little bit too small. So for our purposes, what the t distribution is going to do is it's going to compensate. I'm going to have something a little bit bigger here to make up for the fact that this is a little bit too small. If this is a little bit too small, smaller than this, I'm going to put something a little bit bigger in here, bigger than this, to compensate, and hopefully those will balance themselves out. Now, what do these look like? Well, if the normal is distribution, my bell curve, and you don't even really need to focus on it that much, but if my bell curve, my z distribution, you're pretty used to seeing that. That's my z distribution. What a t distribution is going to look like is it's going to be a little bit flatter, flattening the curve, a popular phrase these days, but it's still going to be symmetric. It's still going to be centered at 0, but now I'm a little bit lower in the middle and a little bit higher in the tails. So where this might have been the z-score that left 2.5% in each tail, I've got to reach out further to find the t-score that leaves 2.5% in each tail. So these t-scores are going to be a little bit bigger than the corresponding z-score. All right. Now, there isn't just one t distribution. There's many, many of them. And so we've got to decide which t distribution to use. Which t distribution to use depends on our new phrase for you, degrees of freedom. And understanding fully what degrees of freedom are, yeah, you'll get a good grasp on it. If you go on to get a master's degree in statistics, you'll get a good grasp of degrees of freedom. But to fully explain it, way beyond the scope of this course, but it's easy to calculate. My degrees of freedom is simply n minus 1. Okay. That tells you which line in the t-table to use. So previously with the t-table, we were only using the top line and the bottom line. Top line depended on how much area we wanted in the tails. Bottom line, those were z-scores. Now, all those numbers in between we're going to start to use. Those are going to be where we make the adjustment to, again, put in a slightly bigger t-score to make up for the fact that the z-score might be a little bit light. Okay. I'm going to plow through an example here. So we have a random sample of hippos. We found the weight of each. Of the 11 hippos, in our sample, we have a sample mean of 3929 and a sample standard deviation of 623. Okay, so it'd be really a hokey assumption to assume we knew sigma. We knew how much weights varied amongst all the hippos in the world, but we do have the 11 hippos in our sample, and we know how much their weights varied. Now, from here, I can find the standard deviation of x bar. That's going to be s over root n. In this case, 623 over the square root of 11. Again, you're better off keeping around more decimal points instead of less. But I'm going to slow down and do this on my calculator, give you time to do the same. And I'm going to take 623 divided by the square root of 11. And again, err on the side of keeping around more decimal places for the moment instead of less. 187.84157. That's probably overkill, but I'd rather err on the side of having too many decimal places than not enough and introducing some rounding error there. Now, what's E going to be? I just erased it. Okay. So let's make a 98% confidence interval for mu. Okay, we're making a 98% confidence interval. So some of this should be pretty boilerplate and easy for you now. For a 98% confidence interval, I'm going to abbreviate confidence interval CI at this point. Alpha, the probability of being wrong is 2%. Alpha over 2 is 0.02 over 2, which is 1%. Probably did that without a calculator, I hope. Okay. Now, what's new here is my degrees of freedom is n minus 1. In this case, I had n was 11. We had 11 hippos that we weighed. So, not too hard to do. We've got 10 degrees of freedom. So, instead of using, well, t of alpha over 2 is now the t-score that leaves 1% in each tail. So I'm going to ask you to take out, hopefully I asked you to print out the t-table before you did the video. I've got highlighted on here the correct t-score to use is 2.764 for 10 degrees of freedom. All right, let me slow down a little bit and show you where we got that now. We're making a 98% confidence interval. And I erased all my numbers. So for a 98% confidence interval, my t distribution looks a lot like the z distribution. It's flatter, it's bigger in the tails, but it looks pretty similar. I'm still going to sketch more or less a bell curve. And I want a t-score that makes this area 98%. Of course, a t-score of 0 is right in the middle. Now, here's the part that messes some people up. The column that we're going to use, if I've got 98% in the middle, I've got 2% in each tail. I'm sorry, I've got 2% total for the tails. I've got an area of 1% in this tail and an area of 1% in this tail. So the way your table is made, the top of the column heading is not 0.98, but it's 0.99 is the one we want. If I'm making a 98% confidence interval, the area to the left of this mark is not 98%. It's this 98% plus this 1%. So I am looking up the column for 0.99. So if you go back to your t-table, so 10 degrees of freedom is the row that we use, 0.99 is the column that we use, and we see the 2.764 is the t-score that leaves 99% to the left of this mark. By symmetry then, well, that leaves 1% in the right tail, and since this is symmetric, negative 2.764 would leave 1% in the left tail. So my error here is going to be the t-score that leaves alpha over 2 in each tail times s of x bar, which is going to be the t-score that leaves 1% in each tail times s of x bar. This is 2.764. And to be completely honest with you, I came in to film this with a little extra time that was available and didn't have it completely prepped ahead of time. And I've erased x bar and I've erased standard deviation of x bar since you have it. But you should be able to multiply this by the standard deviation of x bar. And I forget what I made up along the way, so you will have to figure this one out. And then my 98% confidence interval for mu is going to be x bar plus or minus this E. And I have completely forgotten, and I'm trying to search the shadows here for what I put on there. So I think this is 3929. If not, put in the appropriate number, plus or minus whatever E is. I, at this point, am going to make something up and say it's 705. Again, that's not right. You've got your E over there. But I just want to be able to sort of finish this off and call it 3224 up to 4634. Now again, this is wrong because I foolishly didn't write down what I was doing as I was going along, had to erase the board, don't have a class full of people to ask. So here, whatever I said x bar was. Here, whatever you calculate when you take 2.764 times the standard deviation of x bar, which again we calculated and I erased. The important thing I want to get across here, here's our confidence interval. Now that's a pretty wide confidence interval. Well, here's why it's a very wide confidence interval. One, I was looking for a lot of confidence. I was looking for 98% confidence. But even more so, what made this wide is I was trying to estimate what is the average weight of all hippos in the world based on a random sample of only 11 hippos. So because my sample was so small, I ended up with a very wide confidence interval. Okay. Notice here 2.764, if you went all the way down, you would have seen that the very bottom of this column is 2.326. So the z-score that leaves 1% in each tail is 2.326. Instead of using 2.326, we use 2.764, something bigger. We use this that's a little bit bigger than 2.326 to make up for the fact that this is quite possibly too small. Hopefully those mistakes will balance each other out and we get a reasonable number for the error. What this does and does not mean, because people get confused. People often think that this means that 98% of hippos are in this range. That's not what it's telling you. What we were trying to find was mu. We were trying to find the mean. We were trying to find the average for all the hippos in the world. And we didn't have the time, the energy, or the resources to go find every hippo in the world and then say, excuse me, Mr. Hippo, can we get on the scale here? We would like to weigh you to get our data. So we were only able to get a random sample of 11 hippos. What this is telling us is if we were able to weigh all the hippos in the world, we're pretty sure, we're 98% confident that the average for all the hippos in the world is somewhere between here and here. Okay, so again, it's not that 98% of hippos are between here and here, it's that we're 98% sure that the average for all hippos is here and here. Based on what? Here's what the average was for 11 hippos. We know this probably didn't nail the average for all hippos dead on, so we added and subtracted some error to it, said here's my interval, and I'm pretty sure that mu falls inside this interval.